Welcome, everyone. Your brain is changing right now. Every thought you think, every habit you repeat, every experience you have is shaping the structure and function of your nervous system. For a long time, scientists believed that meaningful brain change was limited to childhood. Today, we know that's not true. The adult brain retains an extraordinary ability to adapt, learn, and rewire itself. In this discussion, we'll explore two of the most fascinating frontiers in modern neuroscience, psychedelics and neurostimulation. We'll examine how these tools may influence neuroplasticity, why they have attracted so much scientific interest, and what they can teach us about the brain's capacity for transformation. Let's begin by understanding a fundamental truth. The brain you have today is not necessarily the brain you'll have tomorrow. One of the most important concepts to understand when discussing brain change is that the nervous system is not simply a recording device. It is not passively collecting information from the world around you. Instead, it is constantly evaluating, predicting, adapting, and modifying itself based on what you repeatedly think, feel, and do. Every experience you have leaves a biological footprint. When you learn a new skill, form a habit, experience stress, recover from adversity, or repeat a behavior over and over again, specific neural circuits become stronger. Neurons that fire together tend to wire together. This principle, often referred to as Huberman plasticity, is one of the foundational mechanisms through which the brain changes itself. Think about learning to ride a bicycle. The first time you attempted, the movement feels awkward and unstable. Your brain is trying to coordinate balance, vision, muscle activation, and spatial awareness simultaneously. But with repetition, those neural pathways become more efficient. The behavior requires less conscious effort because the circuits involved have been strengthened through practice. The exact same process occurs with emotional patterns, thought patterns, and behaviors. If someone repeatedly experiences anxiety in response to certain situations, the neural networks associated with anxiety can become increasingly efficient at generating that response. If someone repeatedly engages in self-defeating thinking, those pathways can become deeply ingrained over time. The brain does not necessarily distinguish between useful patterns and harmful ones. It simply reinforces what is practiced consistently. This is why habits become automatic. It is also why change often feels difficult. You're not just attempting to alter a behavior. You're attempting to modify biological pathways that may have been reinforced thousands of times. What's fascinating is that the brain remains capable of change throughout life. For many years, there was a widespread belief that neuroplasticity largely disappeared after childhood. We now know that's not true. While certain forms of plasticity are heightened during early development, the adult brain retains a remarkable ability to reorganize itself. However, adult plasticity is different from childhood plasticity. Children absorb information almost effortlessly because their brains exist in a highly adaptable state. Adults, by contrast, require attention, motivation, repetition, and often a degree of challenge or discomfort to trigger significant neural change. This is where the concept of focused attention becomes critically important. Attention acts like a spotlight for the nervous system. Whatever you consistently direct your attention toward becomes more likely to influence neural architecture. When attention is combined with emotional significance, the effect becomes even stronger. This is why emotionally charged experiences are remembered more vividly than ordinary events. The brain interprets emotional intensity as a signal that something important is occurring. Neurochemicals such as norepinephrine and dopamine help mark those experiences as relevant, increasing the likelihood that neural connections associated with them will be strengthened. In many ways, learning is not simply about acquiring information. Learning is about changing the structure and function of neural circuits, and that process requires energy. The brain is constantly balancing stability and adaptability. If neural circuits change dramatically every moment of every day, you would never develop consistent skills, memories, or behaviors. At the same time, if the brain were completely rigid, learning would be impossible. The nervous system solves this problem by creating periods in which plasticity is elevated. During these periods, the brain becomes more receptive to change. New connections form more easily, existing circuits become more flexible, and behavioral modification becomes more achievable. Research suggests that these plasticity windows are influenced by a variety of factors. Novel experiences can increase plasticity, intense learning can increase plasticity, physical exercise has been shown to elevate levels of brain-derived neurotrophic factor, or BDNF, a molecule often associated with neural growth and adaptation. Quality sleep also plays a critical role because many of the structural changes associated with learning occur during deep sleep and REM sleep. What becomes clear is that neuroplasticity is not a mysterious phenomenon. It is a biological process governed by identifiable mechanisms. When people talk about changing their lives, they often focus on motivation. Motivation certainly matters, but from a neuroscience perspective, lasting change depends more heavily on repeated activation of specific neural pathways. The brain learns through action. You cannot think your way into a new neural architecture. At some point, behavior must change. Each time you perform a behavior, you provide the nervous system with evidence that the associated circuit should be maintained or strengthened. Each time you refrain from a previously reinforced behavior, you begin reducing the dominance of that pathway. This process takes time because the brain values efficiency. Existing circuits have often been reinforced for years. Building new pathways requires repetition, consistency, and patience. What's encouraging is that even small changes, when repeated consistently, can produce profound transformations over time. A person who practices focused attention daily can strengthen networks associated with concentration. Someone who regularly engages in deliberate learning can improve cognitive flexibility. Someone recovering from trauma can gradually develop new emotional responses through carefully structured experiences and therapeutic interventions. The nervous system is continuously responding to the signals it receives. Every workout changes the brain. Every conversation changes the brain. Every habit changes the brain. Every challenge changes the brain. Whether those changes move you toward greater resilience or deeper limitation depends largely on what you repeatedly expose your nervous system to. Understanding this principle shifts the way we think about personal growth. Change is not simply a matter of willpower. It is a biological process of rewiring neural circuits through attention, experience, repetition, and behavior. And once you understand that the brain is designed to adapt, you begin to recognize that many of the patterns you once considered permanent may simply be well-practiced pathways waiting to be reshaped. To understand why psychedelics have generated so much interest in neuroscience and psychiatry, we first need to understand what normally happens inside the brain when information is processed. Under ordinary conditions, the brain relies on established networks that help create a stable perception of reality. These networks allow you to predict outcomes, recognize familiar patterns, make decisions efficiently, and maintain a coherent sense of self. This efficiency is incredibly useful. Without it, everyday life would become overwhelming. However, the same mechanisms that create stability can also contribute to rigidity. The brain develops preferred pathways for thinking, feeling, and behaving. Over time, these pathways become increasingly automatic. In some cases, this is beneficial. In other cases, it can contribute to persistent anxiety, depression, addiction, compulsive behaviors, or deeply ingrained negative beliefs. One of the most intriguing findings in modern neuroscience is that certain psychedelic compounds appear capable of temporarily disrupting these rigid patterns of activity. Rather than forcing the brain into a completely different state, they seem to reduce the dominance of highly established networks, allowing communication between regions of the brain that do not typically interact as extensively. Research involving compounds such as psilocybin has shown changes in large-scale brain network connectivity. During these altered states, the brain often demonstrates increased communication across different regions, creating a more flexible pattern of information exchange. Instead of relying on the same familiar routes, neural activity appears to explore alternative pathways. This is significant because many psychological challenges involve repetitive loops of thought and behavior. Individuals suffering from depression, for example, often experience persistent negative thinking patterns that become difficult to escape. The brain repeatedly activates the same circuits, reinforcing the same emotional and cognitive experiences. When network flexibility increases, there may be an opportunity for the nervous system to temporarily step outside those established patterns. This does not automatically solve the underlying problem, but it can create conditions in which new perspectives become possible. One way to think about this is to imagine a forest with a well-worn trail running through it. The trail has been used so frequently that it becomes the default route. Every time someone enters the forest, they naturally follow the same path because it is familiar and efficient. Now imagine that for a brief period, the forest opens up. Suddenly, there are many potential routes available. People can explore areas they rarely visit. New paths can be discovered. The original trail still exists, but it is no longer the only option. Something similar may occur in the brain during states of enhanced plasticity. Another important aspect of psychedelic research involves molecules associated with neural adaptation. Studies suggest that certain psychedelics may influence processes linked to neuroplasticity, including increases in factors related to synaptic growth and neural connectivity. Scientists have become particularly interested in brain-derived neurotrophic factor, often called BDNF, because of its role in supporting the growth, maintenance, and modification of neural circuits. While the exact mechanisms remain an active area of research, evidence suggests that psychedelic compounds may create biological conditions that support learning and adaptation. This is one reason researchers often describe these substances not as treatments themselves, but as tools that may facilitate therapeutic processes. This distinction is extremely important. A common misconception is that a psychedelic experience alone creates lasting change. The scientific evidence suggests a much more nuanced picture. The experience may open a window of increased flexibility, but what happens during and after that window appears to play a critical role in determining long-term outcomes. The brain is constantly asking a simple question: what should I learn from this experience? The answer depends heavily on context. If an individual gains meaningful insights but never changes behavior afterward, many of the old neural patterns may gradually reassert themselves. On the other hand, if the period of increased plasticity is combined with therapy, intentional reflection, behavioral change, and structured learning, the opportunity for lasting adaptation becomes much greater. This is why the concept of integration has become central to modern psychedelic research. Integration refers to the process of translating insights into actions. It involves examining experiences carefully, identifying useful lessons, and implementing changes in daily life. Without integration, even profound experiences can fade into memory without producing meaningful transformation. From a neuroscience perspective, the goal is not simply to have an unusual experience. The goal is to leverage a temporary state of increased flexibility to establish healthier and more adaptive neural patterns. It's also important to recognize that these compounds affect individuals differently. Factors such as genetics, psychological history, expectations, environment, emotional state, and social support can all influence outcomes. This variability is one reason why researchers place significant emphasis on controlled settings and professional supervision. The setting in which an experience occurs can strongly influence the way the brain interprets and responds to that experience. The nervous system is highly sensitive to context, particularly during periods of elevated plasticity. What emerges from this research is a broader understanding of how change occurs in the human brain. Lasting transformation rarely comes from a single moment. Instead, it comes from creating conditions that allow new learning to occur and then reinforcing that learning through repeated action. Psychedelics appear to offer a unique opportunity to temporarily loosen deeply established neural patterns. They may increase flexibility, enhance emotional processing, and create a biological environment that supports adaptation. But the real rewiring happens afterward, through behavior, reflection, learning, and deliberate practice. The experience may open the door, but it is the choices made after that experience that determine whether new neural pathways become lasting features of the brain. In that sense, the most powerful component of brain change is not the compound itself. It is the nervous system's extraordinary capacity to learn, adapt, and reorganize when given the right conditions and the right direction. When most people think about changing the brain, they immediately think about psychology, behavior, or perhaps medication. But over the last several decades, neuroscience has developed another fascinating approach, directly influencing neural activity through carefully targeted stimulation of specific brain circuits. To understand why this is important, it's useful to remember that every thought, emotion, memory, and behavior emerges from patterns of electrical and chemical activity within networks of neurons. The brain is fundamentally an electrochemical organ. Neurons communicate through electrical impulses, and those impulses determine how information flows through the nervous system. In a healthy brain, these patterns of activity remain dynamic and adaptable. Different networks become active depending on what you're doing, thinking, or experiencing. However, in certain conditions, some networks can become either excessively active, insufficiently active, or poorly coordinated with other regions. When that happens, the result can manifest as depression, anxiety, obsessive thinking, addiction, chronic pain, or difficulties with attention and emotional regulation. The goal of neurostimulation is not to override the brain. Rather, it is to influence neural activity in a way that encourages healthier patterns of communication between circuits. One of the most extensively studied forms of neurostimulation is transcranial magnetic stimulation, often called TMS. This technology uses magnetic pulses delivered from outside the skull to influence activity in targeted regions of the brain. Unlike invasive procedures, TMS does not require surgery. The magnetic field passes through the scalp and skull and induces small electrical currents within specific neural tissue. What's remarkable is that researchers can target areas associated with mood regulation, attention, decision-making, and emotional processing. By repeatedly stimulating these circuits over multiple sessions, it becomes possible to encourage changes in how those networks function. Consider depression as an example. Neuroimaging studies have shown that certain regions involved in cognitive control and emotional regulation may display altered activity patterns in individuals suffering from major depressive disorder. Some networks become overactive while others appear underactive. The communication between regions can become less efficient, contributing to persistent negative thinking and emotional distress. Through repeated stimulation of carefully selected brain areas, researchers aim to shift those patterns toward a healthier balance. The stimulation itself is only part of the process. What makes it especially interesting is the possibility that repeated activation may promote neuroplasticity, allowing the brain to reorganize and strengthen more adaptive pathways. In many ways, neurostimulation can be viewed as a tool that helps guide the nervous system towards states that support learning and change. Another important concept is that the brain operates through networks rather than isolated regions. While scientists often discuss specific brain structures, no single area works alone. Every thought and behavior emerges from communication among multiple interconnected systems. This means that stimulating one region can influence activity across broader networks. A relatively small change in one node of a network can alter information flow throughout the entire system. Think of a large transportation network connecting multiple cities. If a major intersection becomes blocked, traffic patterns throughout the system are affected. Conversely, improving flow through a critical intersection can enhance efficiency across the entire network. The brain functions in a similar way. By influencing activity in strategic locations, neurostimulation may help restore more effective communication among interconnected neural circuits. Researchers are also exploring other forms of non-invasive stimulation. Techniques involving weak electrical currents applied through the scalp are being investigated for their potential effects on learning, memory, attention, and rehabilitation. Although these approaches differ in methodology, they share a common objective: influencing neural activity in ways that support adaptive change. One reason these technologies generate excitement is that they offer a level of specificity that traditional approaches sometimes lack. Behavioral interventions influence the brain indirectly through experience and learning. Medications often affect broad neurochemical systems throughout the brain and body. Neurostimulation, by contrast, allows researchers to target particular networks with increasing precision. That does not mean neurostimulation is a magic solution. The brain is far too complex for simple fixes. Lasting change still depends on neuroplasticity, behavior, and experience. In fact, one of the most promising areas of research involves combining neurostimulation with learning-based interventions. The reasoning is straightforward. If stimulation temporarily increases the readiness of a neural circuit to change, then engaging that circuit through purposeful behavior may enhance the likelihood of lasting adaptation. Imagine teaching a muscle to become stronger. Simply activating the muscle occasionally is unlikely to produce dramatic results. However, if activation is paired with structured training, repetition, and progressive challenge, meaningful change becomes possible. The same principle may apply to neural circuits. When the brain enters a state that is more receptive to modification, learning experiences can have a greater impact. This is why many scientists view neurostimulation not as a standalone intervention, but as a catalyst that may amplify the effectiveness of other forms of training and therapy. What's especially fascinating is that these technologies are providing new insights into how flexible the adult brain truly is. For much of scientific history, the nervous system was viewed as relatively fixed after development. Modern neuroscience paints a very different picture. The adult brain remains capable of remarkable adaptation. Neural pathways can strengthen. Communication patterns can shift. Behavior can change. Emotional responses can be modified. The existence of neurostimulation technologies highlights a fundamental principle of neuroscience. The circuits responsible for thoughts, feelings, and behaviors are not static structures. They are dynamic systems that can be influenced, reshaped, and optimized under the right conditions. As researchers continue refining these tools, the broader lesson becomes increasingly clear. The future of brain health may not depend solely on treating symptoms. It may involve understanding how to deliberately guide neural circuits toward healthier patterns of activity and then reinforcing those patterns through experience, learning, movement, sleep, and behavior. Ultimately, neurostimulation represents another example of a central truth about the nervous system. The brain is constantly changing. The challenge is learning how to direct that change in ways that improve cognition, emotional well-being, resilience, and overall quality of life. When we look at the future of brain rewiring, it's tempting to focus on the technologies, compounds, and interventions that attract the most attention. Psychedelics, neurostimulation, advanced imaging systems, artificial intelligence-driven diagnostics. These developments are certainly exciting. But if we step back and examine the underlying neuroscience, a much more important principle emerges. The future of brain change is not about finding a single tool that transforms people overnight. It is about understanding how to create conditions in which the brain becomes more capable of learning, adapting, and reorganizing itself, and then using those conditions strategically. The nervous system evolved to change through experience. Every meaningful adaptation in your life has occurred because the brain interpreted certain experiences as important and modified its circuitry accordingly. What modern neuroscience is beginning to uncover is how to intentionally increase the efficiency of that process. One concept that continues to gain attention is precision neuroplasticity. Instead of broadly attempting to improve overall brain function, researchers are increasingly interested in targeting specific neural circuits associated with particular behaviors, emotions, and cognitive functions. For example, the neural pathways involved in fear learning are not identical to those involved in attention, motivation, or memory formation. Different networks contribute to different aspects of human experience. As scientific understanding improves, interventions can become more focused and individualized. This shift represents a major change in how brain health is approached. Historically, many treatments were designed around symptom categories. A person might be diagnosed with anxiety, depression, or addiction and receive a standardized intervention. While these approaches have helped many individuals, neuroscience increasingly suggests that two people with similar symptoms may have very different underlying neural patterns. The future may involve identifying the specific circuits contributing to an individual's challenges and then applying targeted strategies to modify those networks. What's particularly exciting is that this future extends beyond clinical populations. The same principles that help restore healthy function can also support learning, performance, creativity, resilience, and cognitive development in healthy individuals. At the center of all of this is neuroplasticity. No matter how advanced technology becomes, lasting change still requires the brain to physically alter its structure and patterns of communication. There is no way around this biological reality. Neural circuits must strengthen, weaken, reorganize, or establish new connections. This is where many people misunderstand the process. They assume that if a tool increases plasticity, the work is complete. In reality, increased plasticity is simply an opportunity. A window opens. What happens during that window determines the outcome. Imagine softening a piece of clay. The clay becomes easier to shape, but it does not automatically form something useful. The final result depends on how the material is molded during that period of flexibility. The brain operates in a remarkably similar manner. Whenever plasticity increases, whether through intensive learning, exercise, sleep optimization, psychotherapy, neurostimulation, or other interventions, the nervous system becomes more receptive to change. But it is behavior, experience, and repetition that ultimately determine the direction of that change. This is why lifestyle factors remain among the most powerful tools available for brain optimization. Sleep is a perfect example. During sleep, the brain performs essential processes involved in memory consolidation, synaptic remodeling, emotional regulation, and learning. Experiences from the day are reorganized and integrated into existing neural networks. Without sufficient sleep, many of the changes initiated during waking hours fail to stabilize. Exercise provides another example. Physical activity increases blood flow, influences neurotransmitter systems, supports the release of growth-related molecules, and promotes conditions that facilitate neural adaptation. Regular movement affects not only physical health, but also cognition, mood, learning capacity, and resilience. The same principle applies to deliberate learning. Whenever you challenge yourself with a new skill, language, instrument, or complex cognitive task, the brain is forced to build and strengthen new neural pathways. Learning itself becomes a form of brain training. Social interaction is equally important. Human beings evolved within social environments, and many neural systems are deeply influenced by relationships. Positive social connection can affect stress regulation, emotional processing, motivation, and even cognitive performance. Future neuroscience will likely continue revealing just how profoundly social experiences shape the architecture of the brain. Another area receiving significant attention involves the interaction between technology and personalized brain training. Advances in wearable devices, neural monitoring systems, and machine learning may eventually allow individuals to receive highly customized feedback about their cognitive states. Rather than relying solely on subjective impressions, people may gain access to objective indicators of attention, stress, recovery, learning readiness, and emotional regulation. This could create opportunities to optimize training schedules, therapeutic interventions, educational programs, and performance strategies with unprecedented precision. However, despite all these innovations, one principle remains unchanged. The brain learns through action. No technology can replace the fundamental requirement for engagement. No device can perform adaptation on your behalf. No intervention can permanently rewire circuits that are never used. The nervous system continuously evaluates behavior and allocates resources accordingly. Pathways that are activated repeatedly become stronger. Pathways that are neglected gradually weaken. This means that the future of brain rewiring is likely to involve a combination of approaches rather than a single breakthrough. Biological tools may enhance plasticity. Technology may improve precision. Therapeutic methods may become more effective. Educational systems may become more individualized. But the core mechanism will remain the same. Experience shapes the brain. Attention directs learning. Repetition strengthens circuits. Behavior determines which neural pathways survive and which fade away. As neuroscience continues to evolve, perhaps the most empowering realization is that the brain is not a fixed structure waiting to be repaired. It is a dynamic system designed to adapt throughout life. The emerging tools of modern neuroscience may help accelerate and guide that adaptation. But the true engine of transformation remains the remarkable capacity of the human nervous system to learn from experience and continuously become something different than it was before. As we conclude, remember that brain rewiring is not about finding a miracle solution. It is about understanding the biological principles that allow change to occur and then applying those principles consistently. Whether through learning, exercise, sleep, therapy, neurostimulation, or emerging scientific tools, lasting transformation always depends on neuroplasticity, the brain's remarkable ability to adapt. The most important takeaway is simple. Your nervous system is not fixed. It is constantly responding to how you think, what you do, and what you repeatedly practice. The future of neuroscience is helping us understand how change happens. The opportunity is deciding what we choose to become. Thank you for listening. I'll see you in the next one.